recording right now. And here we are with day 2 of binary trees. And I'm going to start out today with going back to what we were doing on Tuesday. Let me make sure this is up. This is up so I can see what I'm doing. Can you see that? Everybody's good?
Yeah.
Okay. So one of the things that we didn't get to on Tuesday was how to delete a node from a binary tree. So the first thing I want to do is I'm trying to think of a good word that we could build a binary tree with. And, you know, like the other day we did Harrisburg. So why don't we start today with Pennsylvania. Pennsylvania. And build a binary tree with the word Pennsylvania. Okay, remember we had the in order, the pre-order, and the post order, also known as infix, prefix, and postfix. And which one of those gave me the alphabetic interpretation of this? Do you remember?
In order.
In order, in order. Okay, so we can check out in order in a little bit, and then we're going to talk about deleting a node from this. So I'm going to start out. I got a P. That's my root. We talked about parents. We talked about children. We used terms like nodes, leaves, roots, and so on. So after the P, I'm going to go to the left with the E. So far, so good. Where's an N going to go?
To the right of E.
To the right of E. Thank you. Where's the next N going to go?
To the right of N, I guess.
I hear to the right of N. Okay. Where will the S go?
To the right of P.
To the right of P. I'm going to wait you all out. Where will the Y go?
To the right of S.
To the right of S. L.
To the left of top end.
To the left of the top end. V.
To the left of S.
And A.
Left
V
of E.
needs to be to the left of Y.
Yeah, I screwed that one up.
This will be on YouTube, so everybody's going to know you screwed it up. After the A, where's the N go?
To the right of the second N.
To the right of the second N. Where does I go?
To the right of A.
To the right of A. Is it less than E? Or greater?
Yeah,
I'm coming over here. Less than N?
Yeah, left of L.
Left of L. And finally, one more A.
Right of A.
Right of A. Okay. How many levels? What's the height of this tree?
5.
5. How many leaves? A leaf points to 2 nulls.
4.
4, yeah, the A, the I, the N, and the V. We don't have anything there. And again, these would all point to nulls. So I would have a null here, a null here, a null here, 2 nulls there, a null there, a null there, 2 nulls there. This would be a null. Lots of nulls. Lots of seemingly wasted space. Okay, so let's just run through. We said if we try infix, it should give it to me in alphabetical order. Infix. Making a little note over here. 4 plus 3. Infix was left, node, right. I come to here, I go to the left. I come to here, I go to the left. I come to here, there is no left, so I go back to the node, and now I go to the right. There is no left, I come back to the node, and I go to its right. Now that I'm done, I traverse back up, and I should hit the E, which was my node, and now I go to the right. Is there a left? Yes. Is there a left? Yes. So I get the I, go back to the node, get the L. There is no right. Go back to the node. There's a right. Check its left. There's nothing. Go back to the node. Check its right. No left, node, no right. So now I traverse all the way back up to the P. I'm down to the node. Is there left? No, because we screwed that one up. Go back to the node, S. Go to its right. Is there left? Yes. Go back to the node, Y. Huh? Easy? Yeah, man, that's easy. Okay, good. Which one did we have the most trouble with the other day? Was that the prefix or the postfix?
Post.
Post. Let's do this one in postfix as well. This was null. Null. Postfix was left, right, node. Again, the only thing that moves is the node. So I want the left, then the right, then the node. I want the left. I want the left. There is no left. I want the right, which is an A, and then I want the node. I took care of this guy's left. Now I'm coming to the right, coming to the left, coming to the left. I get I. I check out its right. There's nothing. I go back to the node. Now I'm back up at the end. So I took care of the A, the I, the L. Coming down, I hit his right. I check left. I check right. I get node. I took care of this guy's left. I took care of his right. So I come back to the node. I took care of this guy's left, his right. I come back to the node. AAILNNE. Am I off to a good start?
Yeah.
Okay.
Got an N.
Did I forget an N? Yes, I did forget an N. It's going to be in here somewhere. Thank you. Took care of the left. Now I come to the right. I look to his left and I go to his right. I looked at his left. I get a V. Look to his right. Go back and get the node, which is Y. Took care of his right. Go back and get the node, which is an S. And finally a P. Cool? Questions?
Okay, it seems explanatory.
Seems easy, yeah. Yeah, it's one of those, it's, a lot of times stuff is easy when someone's in front of you explaining it and you're following along. Y'all want to do prefix real quick, or you think you got it? Okay, then. All right. So I said, now that we did a quick review of what we did on Tuesday, I said we want to take a look at delete. And I'm asking for test data. What would you like to delete from this? Because when we think test data, then we get a pretty good idea of how to write the code. So what would you like to do?
Delete the P.
Okay. I'm going to leave that as the second one because what should I check first?
You.
Nope. What should I check first?
One of the leaves.
ISEMPTY. Okay.
So
Good. All right. So now I want to get rid of P, which is the root. Give me something else to delete.
the first N.
The first N. So you're looking at, describe why you picked the first N.
It just looks fun.
It looks fun. Yeah. I'm going to say E, just so we don't get confused because there's multiple N's. I'm going to say E because what's going on with E? It has 2 children. It has the A and the N. What else would we want to delete?
I.
I would go with that because it is a leaf. And I guess if we're going to delete something with 2 children, we should probably talk about deleting something with 1 child, maybe like S. So delete. Let's talk about it. Is empty piece of cake, right? We don't have to do any worrying about is empty. Capiche? Oh, let's see. If I delete P, whatever I do with P is going to kind of be the same as whatever I do with E, because again, it's 2 roots. So let's just jump on E right now. What would happen if I wanted to delete E? Well, this is going to sound bizarre, but here's what we would have to do. If I wanted to get rid of E, I would now have to rotate. I'm going to take this N and move it up to that spot. So that's first. And then I would have to take this L and rotate it. Since it's less than N, it's now going to not be on, it still has to be on the left side of N. So this whole subtree is going to have to come over and be the rightmost child. So it's kind of funky looking, but it would have to attach to the rightmost node's rightmost child in order to maintain my binary search tree, so that if I did an infix, I would be able to get it in alphabetical. Okay, so P that used to point to E now will point to N, and then N will point to A, and then the rightmost one, A, will now point over here to catch the rest of it. So N's left child is A, N's right child would be N. Yeah. Sounds interesting. If I wanted to delete I, what would I do to it? I checked it and I see both of its children are null.
Oh,
So all I have to do is make its parent point to a null. That wouldn't be too bad. One leaf, like if I had L and it only had 1 child, think you can see what's happening. I would just have the N point to the 1 child, be it either I, or if it was on the right side, what's over here. So as much as I think it would be fun to sit and write the algorithm to do all this, instead I want you to go back and pull up binary in, or what we had last time, binary entry and so on, and grab what was it, 21.4, and load it up. Let's take a look at it. There we go. Can you all still see my screen?
Yeah.
Or
Yeah.
do you just see me doing stuff?
It's the paper on the screen.
Okay. All right. Because my one class yesterday, this is where I messed up. Trying to share what's on my laptop machine. And let's see how cool I am. If I take this and I switch to this, you have that. And now if I want to share my screen, I share this. And did it share my screen? You can see 21.4 on my screen?
Yeah.
Okay. So in this program, we had insert, we had all kinds of stuff going on. What I want to take a look at is in intBinaryTree.cpp, what the heck does delete look like? So it looks like I have something called delete a node, and we want to get ready and to delete it. Let's see what's going on here. If num is less than node value, call delete node again. Else if num is greater than node value, call delete node again, else make deletion. And all of a sudden I see a whole block of code of how to make a deletion. Line 123, we talked about reattaching the left child. Line 129, we talk about reattaching the right child. Remember when I said if we're deleting something that has two children, how we would have to go about the reattach? If you look down here, if the node has two children. So we have a couple of things going on in here. Code that we would probably spend a whole class doing the algorithm for, but it's already done and it's given it to you, so we don't have to do that. Any questions on that? So now you have this whole big int binary tree, and these are all basics, and you're ready to get to use them. Screen sharing has stopped to share. The window is closed. Okay, I got it. So now I want to go and share. Moving on. The next thing would be, oh, I can't find it. Here, share, but I want to go to this. All right. So binary trees are common more than you think than you might think. What is it you see in front of you? Hopefully the same thing I see in front of me. Somebody
That Morse code?
Yeah, you see the Morse code, okay? And we've done some things that really lead us into this Morse code, because somewhere you wrote a program for the most frequent letters in a big paragraph. Well, I'm guessing way back when they first developed Morse code, they took a gigantic block of words or documents, and what letter do you think they found to be the most common letter?
E.
E, okay? And I'm willing to bet that T is right up there as the second most common one. And so according, in wartime, they're looking to do this Morse code as simple as possible, meaning with as few characters as possible. Now imagine the dots as 0 and the dashes as 1. Could we quickly convert Morse code into binary for us? So if I gave you the letter, or if I gave you the dot dot dash or 001, what letter would that represent?
U.
U. Okay, it would go down that chart. So here's another example of a binary tree, like I said, that kind of makes sense now that I'm looking at it, now that I'm thinking of it as a binary tree, now that I'm thinking of it as, what are the most frequent letters? You look across that bottom line, you see Z and Q and X and V, and yeah, these are probably the fewest used letters back during that time. Questions? We all good? And then there's other things. Did any of you ever have that little blue, it's like a round ball shape, and it's a game, and it says, I can guess your animal in whatever number of guesses, and you start asking, it starts asking you questions. Does it have, is it on land or is it in the ocean? And it'll do something, you'll say ocean, and then it'll ask you two more choices, and it's basically breaking it down so you can get an answer following this whole binary tree kind of deal. Okay, if you have, let me see if I can get back to my screen now. If I hit stop sharing, is that going to work? Yep. Am I back on your screen? Say yep. Yep. Okay. I'm taking a look in the NIOF book right now. So if you want to grab the NIOF book, the next thing we're going to talk about is a little bizarre, and I'm going to start with a new word, and let's go back to building a binary tree with the word objects, since that's what I have right in front of me. Pow. OBJECTS. I got an O. From the O, where do I go? Well, I have a B. It looks like I'm going to the left. And again, I got to stop that. I ask a question and then I end up answering it. Where do I go with J?
To the right of B.
To the right of B. Where do I go with E?
To the left
Left
of
of
J.
J.
Left of J. Very good. C.
To the left of E.
Boy, this isn't the most optimal word I could have picked. T.
Right of O.
And S.
Left of T.
Okay, so we built objects really quick. First word I could come up with just because I saw a textbook. Now, we're dealing with a binary tree, and up to this point, we looked at it as a linked list kind of deal, where I have a node and I'm going to the left and I'm going to the right, and it all seems to match up. Well, this also could be represented in all of its bizarreness as an array. Oh boy. How big am I making this? Okay, what do I mean it could be done in an array? Well, each one of these locations in my binary tree could be represented by a number. And if I take a look at the root, I might want to represent that as the number 0, which means down in my binary tree, I would store the O because that's sub-0. B would be 1. T would be 2. What would go in 3?
J.
Nope. Because what happens if I later wanted to insert the letter A? Where would that go? Well, the A would go over here if I wanted to insert one. So what location would the A be?
3.
3, yeah. So right now we don't have anything there. So we're going to let the subscript 3 blank. J is going to go in 4, 5, 6. So some of these are blank. So if I'm looking, 3 is blank, 4 has a J in it, 5 has an S in it, 6 is blank, 7, 8, 9, and I would keep going on. So it looks like 6, 7, 8, 9, 10, 11, 12, 13, 14. What's starting to happen here? I am wasting a lot of memory. I would need a size 19 to get to the C. But my question is, and the answer is yes, could I represent this by using subscripts, storing it in an array? Again, we don't like arrays because it uses up a lot of memory, but I could use it. So now the question is, if I have a parent, where's its children? If I have a parent, where are its children? So let's take a look at an example. If I have a parent, it's 2, its children are at 5 and 6. If I have a parent 4, its children are 9 and 10. If I had a parent N, where would its children be?
Two n plus 1 and 2n plus 2.
Everybody like that? 2n
Yes.
plus 1 and 2n plus 2. Looks good to me. Good. What if I was a child? Where is my hairbrush? Where is my parent? If I'm a child and I'm at 3, my parent is at 1. If I'm a child at 4, my parent was at 1. If I'm a child at 11, my parent was at 5. If I'm a child at N, where's my parent?
N minus 1 over 2.
N minus 1 over 2. Does everybody like that?
And n minus. Oh, yeah, that's true. Yeah, that's
I
it.
think it depends if it's
It
even or
depends
odd,
if
though.
you're left or right, I guess.
Okay, if I plug in 3, 3 minus 1 is 2, 2 divided by 2 is 1. If I do 4 minus 1, I get 3, 3 integer division 2 would in fact give me 1. So we are thinking as if I had to program this, I would want to be using the integer division. So yeah, I'm okay with the n minus 1 over 2. Cool? Questions? Okay, now this is something we're not going to use right now, but it comes up right now, so it's important to cover it. We are going to come back to this later, and I'm going to ask you for these formulas again, because they're not going to go away. All right, a couple more things we want to cover yet. Terminology-wise, the next term I want to take a look at is on page 656, and it's what's called a complete tree. So if you happen to be on that page, you'll notice that a complete tree is all levels are filled except bottom row, which is filled starting on the left. All right. So if you're on page 656, you start to see some trees that are filled. We have boom, 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 and boom. That's a complete tree, okay? Here to here to here to here to here to there. That's not a complete tree. These levels are filled, but the bottom row isn't filled from the leftover. Questions on what a complete tree is. Terminology we'll use later when we're working on some things. We'll say the blah, blah, blah has to be a complete tree. And our second definition is what's a balanced tree. Okay, balanced tree has a definition on page 657. And here's kind of what a balanced tree looks like. Okay, now a balanced tree is we're going to take the difference in the size or the levels to the left subtree and the levels to the right subtree. So if I start at my root, what's the height of the left subtree? 2. Okay, what's the height of the right subtree? Can everybody still hear me?
Yeah.
2.
Okay, I heard it ring. So what would it be for this tree? 2 minus 2 is 0. So we're looking at left subtree minus right subtree. And when we do that, we want the following numbers, either 0, -1, or 1. So when I took the left subtree minus the right subtree, I got a 0. If I start here, what's its left subtree minus its right subtree? This guy's height is 1. This guy's height is 0. So that makes this a 1. If I take a look here, what about this guy? 1 minus 0 is 1. This would be 0. This would be 0. So this is something we would call a balanced tree. Take a look at another example. Is this a balanced tree? If you went and filled in each node, would you in fact have the number 0, -1, or 1 for each one of these?
No.
Said with great confidence. Let's
No.
see, 1, 2, 3, 1, 2, 3. My root would be 0. It would have a balance factor of 0. This first left node has a balance factor of what? 2. 1, 0. This guy, what would his balance factor be? This node right here.
Is that 3?
I'm going to say -1. What's the height of his left subtree is 1. The height of his right subtree is 2. So 1 minus 2 is -1. What about this node? Well, this guy we know is 0. This guy is 0. What do we know about this one? What's its
1.
left subtree?
0.
0. Its right is 1.
1.
0 minus 1 is -1. So this guy is pretty close to being balanced. My problem is right here. And eventually later, so if you think of it as an array, we're starting to waste a lot of memory space. One of the things eventually you'll see is we can make this balanced by, we're going to rotate this guy, move this guy here up, move him down to the right, and so on. Don't worry about that right now. So we have a balanced tree and a complete tree.
So it's balanced if the rows cancel out row by row, or if the left and the right cancel out.
If the difference in the subtrees is the height of each subtree is 0, -1, or 1. All of these are good. There's zeros and -1, except this guy.
Gotcha.
He screws me up and we say, nope, it's not a balanced tree because it was 2 minus 0 for him.
Gotcha.
Okay. All right. You want to type. I know you want to type. So let's get back to what I want you to do. You have your ever popular int binary tree, right? And you have 2.4, which has a demonstration with a whole bunch of stuff. Here's what I'd like you to add to it. I'd like you to add a function that counts the nodes. Is everybody okay with that? What I mean by count the number of nodes?
Yep.
Yep, okay. Second thing I want you to do is count the leaves. Little side note, how do I know it's a leaf?
Has no children.
No children, right? We see 2 nulls. And the third thing I want you to do is tell me find the height of the tree. All of these sound really easy, but guess what? They're not. So here's what I want to do. I'm going back to my gallery view, and I have something called breakout rooms. And it says assign 9 participants to 1 room. I don't have to do that automatically. No. Never mind. I didn't really know what breakout rooms was to use it. So I'm going to stop the recording, and you have about 38 minutes to take care of these. You can stay on and work on them. I'm trying to figure out a way to get us to work in pairs so that we can still see each other, and maybe one person can share a room. So let me stop the recording first.